Welcome to Global Wind Systems Part 1, Chapter 10. So let's get started. So at the end of this online lecture, you should have a better understanding of the atmospheric conditions, the cause and effect of what we call the single cell model, the three cell model, and real world semi-permanent highs and lows. Okay, so the general circulation in the atmosphere. This is just a representation of the average airflow. What causes this airflow? Well, it's the unequal heating of the Earth's surface. What is the cause of this unequal heating? From Chapter 3, we learned that the cause was the Earth's surface is curved. The tropics experience a net gain of energy, and the poles experience a net loss of energy. And the other things that we learned is that how does nature correct for this imbalance? Well, the atmosphere transfers the warm air towards the poles. To develop a better understanding of this, we need to develop some models. These models will try to eliminate some of the complexities of the general circulation. So the first model is what's called the single cell model. So the simplifying assumptions of the single cell model: Earth's surface is uniformly covered with water. So why do we want to do this? The reason is it simplifies the system. We don't have to worry about land. And we're going to put the sun directly over the equator. Why are we doing this? Well, again, the sun is not always directly over the equator, so we're simplifying our system to see if we can find some answers. And again, the Earth does not rotate. The rotation complicates the system, so we want to reduce the complexity to help us get some better understanding of the system. So what happens is this, since right here is the equator, that's where all the hot air is, and what happens when air gets hot? It rises, and so it'll rise up at the equator, flow along these lines, and then eventually it'll start cooling down, and when it gets to the poles, it'll come back down and then come back around the surface, start warming up again, and get back to the top. It'll do this in both halves, the northern and southern hemisphere. It also will do it on both sides here. This is a three-dimensional process. So what you have to think about is this is a ribbon of air that wraps around each hemisphere. Okay? So now we're going to complicate our model a little again. We're going to go into what's referred to as a three-cell model. So we're going to make the Earth rotate this time, so we're going to add that complexity. Well, what will this do? It's going to complicate our system. We're going to, instead of having one big cell, which was called the Hadley cell, that's a thermally driven system, it's going to create three cells. All right? So we have these three cells. We have our one we had before, the thermally driven system. Okay, and then here, and it's called the Hadley cell. And then we have this polar cell, and it's also a thermally driven system, like that. Okay, and same reason, as cold air is over the poles, the air is going to want to come down and flow this way along the surface, and eventually it's going to warm up and go up higher. Same region here, except the warm air is around the equator. That's going to cause the air to rise. It's going to rise up, hit the top of the atmosphere, run along it, and then cool off and come back down. Now what this third three-cell model does, by just adding the rotation there, it creates this what's called a Ferrel cell, and that's a mechanically driven cell. And what do I mean by mechanics? Well, the air here is flowing down. Okay, so that's going to bring any air around it down also. So that starts the Ferrel cell. and then that air is going to want to go somewhere. It can't go into the earth, so it's going to fall along the earth, and then it's going to hit the polar cell. And remember, on this side of the polar cell, the air is going up, so this is going to draw that air up, back up, and then draw it around this way, and that is a mechanically driven cell, not a thermally driven cell, as you see in the Hadley and the polar cell. All right, so this 3-cell model breaks into 3 cells like we talked about before. The Hadley cell is between 0 degrees and 30 degrees latitude. The polar cell is between 60 degree latitude and the poles. And all these are thermally driven cells, or what we call convectively driven cells. And then the Ferrel cell is in between the latitudes of 30 degrees and 60 degrees. And this is a mechanically driven cell, or sometimes referred to as a thermally indirect cell. All right, so as these cells move around, it creates highs and lows. So if the air is coming down, that is what we call divergence, right? And so we get a high pressure system at the poles. Now here at 60 degrees latitude, the air is going up. That's called convergence on the surface, and divergence up above, because it's a high pressure up above. And we get these cells here. So we'll get another high here and another low here, another high here, and we get these regions that show up on the globe. And then there are sustained wind patterns in here. So where the polar cell, the winds always want to blow easterly. Again, this adds one more complexity when we have the Earth rotating. So this is our complexity. And so you get these constant easterly directed winds. Now, if you're in the Ferrel cell region, you have these westerly winds. And then if you're in the Hadley cell region, you get what are called the trade winds. These are northeast and these are southeast. And you get a region that they call the ITCZ zone, or for the intertropical convergence zone. And you get both of these, and you get all these regions both in the north and northern hemisphere and southern hemisphere. And these develop the overall climate models that we see. All right, so in the 3-cell model, you get produced what's called a polar front. It is basically the boundary that separates the cold air moving down from the poles and the mild air moving up from the mid-latitudes. All right, so let's make it more of a real-world model. So we're going to bring the land masses back in. And so to do that, we need to take some look at some data and see what it says. And what it's going to end up saying is we're going to see regions where we have pressure systems that persist over time. We call them semi-permanent highs and semi-permanent lows. The highs tend to occur more in the tropical regions where there's warmer weather. So you get this Bermuda high or Pacific high. And the lows seem to be permanent in the colder regions. So you get this Atlantic low or Aleutian low. So let's look at some data. This is for January, the month of January weather. And you can see that you get some highs here in the Pacific and in the Southern Atlantic, Southern Pacific. And the lows appear over land, right? Those are going to be convergence zones, remember. Surface heating, land heats up faster because it has a lower specific heat. So those should produce more lows. Now, when you when you get up in the north, it's a little bit different because we're in winter here, and in the southern hemisphere they're in summer. The sun is not over the northern hemisphere, it's over the southern hemisphere at this point, and it looks a little different. You get the highs now seems to be over land. You get this Bermuda high here and a Pacific high. You get a Siberian high. that can occur up. You get the Aleutian low here over Alaska. You get your Atlantic low over here. Atlantic low, Icelandic low over here near Iceland. And now if we go to the summer I guess I don't have any summer patterns. I believe they're in the book, so you guys can go look at those. All right, so I hope you have a better understanding of the atmospheric circulation, the cause and effects of those using a single cell model and using a 3-cell model. I also hope you have a better understanding of the real world model that shows up, what are referred to as semi-permanent highs and semi-permanent lows. That's all I have for you in this part. I'll see you in part 2.